All righty, what's up, friends? Good to see you all again. All right, so you got some time to play with evaluating limits analytically. So let me give you another one that is just a little bit of a bear. Let's kind of see what you all would do with it. All right, let's make this one. Yeah. What if I gave you something like this? All right, why don't you guys go ahead and pause that and see what you can do with it. All right, so here we go. If I'm plugging it in there, I see 1 over 1, minus 1, and then 1 minus 1. I got a whole bunch of 1s there, but all these 1s essentially are nothing more than just 0 over 0. Well, I am not a fan of denominators, so I'm going to go ahead, even though I see radicals in there, I'm going to go ahead and start off by getting rid of my denominator. I'm going to use common denominators here to see if I can't make this a little bit cleaner on myself. Got an x minus 1 there. And remember, it's the same thing as over 1 and over 1. So I'm going to multiply everybody then by root x. Since I only got one denominator, that's not a big deal. I'll just multiply everybody by root x. And when I do that, I end up with, oh, it's supposed to be narrow. One minus root x all over root x and x minus 1. Well, I'm still in a form that's not great. Still know that if I put my 1 in there, I'm going to be 0 over 0. So what if we keep playing with it a little bit more? Now we did our common denominator. What if we go ahead and combine our rationalizing? I'm hoping that's what you guys did. Don't ever try to get rid of too many things at one time. Just take your time. Sometimes, even though if it takes a little bit longer, sometimes the best things will come. Those who wait, you'll get where you're wanting to get to just a little bit better. So I got root x. I also have an x minus 1 down here. And I also have a 1 plus root x down here. That is an ugly, ugly, ugly denominator. Well, I'll tell you what, if I'm looking at this 1 minus x, I'm thinking to myself, I bet I can factor out a negative 1 out of that. Because I love to have x go first. So if I were to do that, and take my negative out, I'm left with x minus 1. Now I see something that's kind of working out for me a little bit. There's my root x. There's my other x minus 1, so those will go away here in a second. And I have 1 plus root x. And when I simplify it here, I end up with a negative 1 on top, a root x, and a 1 plus root x. So we're going to have a negative 1 over 1 times 1 plus 1, which would be a negative 1/2. So that means that original 1 at the beginning is equal to negative 1/2. So we go ahead and we write that real quick. That was an ugly 1. 1 should be the easiest number to write. And there it is. All right, so that's kind of where we left off last time. And the reason why I left you off there is there's one other interesting little way to rewrite that is, it's kind of cool. It does a little bit of some cool things here. So let me show you another one. It's called the Squeeze Theorem. And here's what the Squeeze Theorem says. We need to do that. There we are. Let's make that longer, make that go out a little bit like this. It says, let's let some function, so we have three functions. Let's take one that h of x, and let's let that be less than or equal to f of x, and I'll add the equal sign here in a second. And let that be less than or equal to g of x for all x in an open interval containing some value x equals c. And I'm going to write some stuff here in a second. Therefore, must exist. Probably wondering, what in the world is he doing? You know, I kind of wonder that myself sometimes. So let's see what we just came up with here. First up, we're going to make these less than or equal to less than or equal. And what I'm saying here, and the limit, I'm going to tell you that there's sometimes some value where we have h of x, where these values actually are equal. So I apparently can't spell. It's going to bug me if I don't fix it real quick. So if these two have to be true, so in other words, the limit when x is at that c value is true for these outside ones, that means the inside one then would make sense. That inside one would also have to be that same value. So we'd say, first of all, this limit also has to exist. So it can't just be sitting out there doing nothing. Since it's between these two and these two exist and equal L, then this one also has to exist, and it also must be equal to that L value. In other words, let's take something like this. See if I can't try to maybe graph this a little something to kind of show you what's going on here. For some value x equals c. And let's say that I have some h of x. Well, I'll make this g of x here. There you are. There's g of x. And we'll make this one h of x right here. And then I have some f of x in between them. And it's always in between or equals to them. So what this is basically saying here is that if I can evaluate the top function, the limit when x is c, and I can evaluate the bottom function when x equals c, and they both equal this L value, that means that middle one, whether I can evaluate or not, also has to be equal to the same thing at that value, x equals c. Let's try this maybe in a different way. What if I told you, let's try this same thing here. We're going to stick with that same idea. What if h of x was this right here, 2 minus absolute value of x plus 4. And let's let g of x be equal to, and again, this isn't a graph, but these are absolute value equations, obviously. One is a v going down, one is a v going up. Absolute value of x plus 4. If I told you, and if I defined these two functions being this, could you then, oopsies, could you tell me what this would be equal to? When x is 4, what is the limit of f of x? So remember what we said. This whole thing right here is still going to be true. H of x is always less than f of x, but f of x is always less than g of x. If we have functions where we know that's true. But here's what the squeeze theorem says. What if, then, I know that h of x is always less than g of x. So let's figure out what h of x is. If this one, I plug 4 into that h of x equation, I'm going to get the value of 2. But notice, if I plug 4 into my g of x function, I plug 4, that should have been a minus there. Sometimes I don't read my own handwriting. If I plug 4 into my g of x function, that's also going to be equal to 2. Well, if I know that the outside function is 2, and I know that this limit for f of x has to be in between them, as Squeeze theorem says, since the lower limit was 2, and the upper limit was also 2, means logic says then that this inside one also has to be equal. Why are you? I am struggling here, friends. Sorry about that. It's supposed to be in. And that inside function, if h of x is 2 and g of x, the limit was 2, then that inside function, that f of x, that middle function, well, that also would have had to have been 2, whether we could have done it or not. This is called the squeeze theorem. It's just kind of a practical idea of what it looks like. But I want to show you guys kind of an interesting little case. You guys can bear with me here a little bit. Okay, so that's the squeeze theorem. You can evaluate the top function, the bottom function, they give you the same thing, then the middle function has to also be the same thing. Well, here's kind of a weird little thing that popped up. I'm going to see if I can maybe make this make sense here. Let me show you guys a little bit different idea. Let's make a circle here. Make that circle purple. Okay. Well, let's just say for the sake of argument that I have a triangle such that it meets somewhere out here. And just for the sake of argument, let's just say that the radius of this thing, the radius of this circle, let's just call it 1. So it's a unit circle, okay? So if that's a unit circle, then this triangle right here is going to be located out here somewhere, where this point right here is some random x and y value. So in other words, I have a triangle. So you guys can see my triangle. I'm going to draw it over here just so you can see it a little bit better. All right. You can all say hi to Julia. She's on the recording now. And
homemade creation. Brownie frappuccino.
Fantastic. So, friends, as we have our y value here, and we have our base of 1 right here. So that's that first triangle. If you notice, this triangle right here, it is inside this sector area. Look at that. See how we got that little sector area? Go back to geometry. Since that triangle's inside this sector, I believe that my sector is going to be bigger than my triangle. So my sector here is going to be something that has a radius of 1. You know? We'll go back and review geometry here in a second, because I got a feeling a few of us maybe we don't remember. So I got a feeling this sector area has to be bigger than this triangle. But what if, just for the fun of it, I build another triangle? It would look like this. Well, now that triangle's clearly bigger than this sector. And if you notice, the base of this triangle is 1, but the height, well, to figure out this height, that's going to be a little different here. So let's think about it here. If I know that this is some theta right here, and I'm trying to figure out the height of that, well, it looks like this is going to be some tangent. So tan of theta is the opposite over the adjacent. In other words, h is tangent of theta. So the height of this triangle would be tangent of theta. And again, we know that that one is bigger than this one. So I have 3 shapes. I know that blue triangle is bigger than the purple sector, and I know that that purple sector is bigger than this red triangle. So let's go through and let's figure out the area of these shapes. This area right here is base times height. So 1 times tangent of theta. Divided by 2. This right here, the area of this triangle is base times height. There we are. Base times height divided by 2. But let's stop there for a second, because I'm not really a big fan of this y value here. So let's go back and let's think about this again. So if this is my y value right here, and the radius here, right here, was 1. That means that would be sine. So sine of theta is y over 1. Or sine of theta is y. So let's get rid of that y there. Let's not use that anymore. Let's call that sine of theta. I got 1 times sine of theta. And again, we're going through here. I know that this right here is greater than the purple, and this right here is greater than that. But we get to this purple. I'm looking at this circle, and let me see here. The area of a circle, the area of an entire circle is pi times r squared. But I'm not taking the entire area. I'm taking some fractional portion of it. Now remember, if we're dealing with radians, it is 2 pi radians all the way around. So the fractional portion I'm dealing with is that angle over 2 pi. So if I were to multiply this by that angle over 2 pi, that means that my pi's would go away. And I'd be left with theta times r squared all over 2. Now let's think about what r squared is, though. In our case here, r squared is 1. So if I were to put 1 in for that radius, turns out this whole area is going to be theta over 2. Well, let's go ahead and play with this and try to clean this up a little bit. I see everything's over 2. So I think if I multiply everything by 2, I might be able to play with something just a little bit more. So let's multiply everything by 2. I'd be left with tan of theta. I'd be left with theta. And a lot of you right now are probably going, Williams, where are you going with this? Just bear with. Bear with. And I see that tangent there, and in my mind, I think that's the same thing as sine over cosine. So I'm going to change that to sine over cosine. And then I have that theta here. And I have sine theta here. So that's over 1, that's over 1. What if now one more time, what if I multiply this whole thing by 1 over sine theta? If that's true, then this ends up becoming 1 over cosine theta. And this would become theta over sine theta. And this would become 1. And again, we know that this is still always greater than the purple, and the purple is always greater than the red. Now, if I were to take the reciprocal of all these, and I were to take every fraction and flip them upside down, that would take my inequalities, and that would make them go the opposite direction. So if I were to flip all these, this cosine theta like that, so cosine theta over 1, this would become sine of theta over theta, and this would still be 1. And these would have got flip-flopped. So now cosine is always less than sine over theta, which is always less than 1. So now here's where we wanted to get to. What if we were to take all these now and we were to take them to a limit of 0? So let's let theta be 0. Let's let theta be 0. Let's let theta be 0. So there's 1. There's sine theta over theta. And then there is our cosine theta. Well, if I take 0 and I plug in for cosine theta, cosine of 0 would be 1. If I plug 0 in here, I ought to get sine of 0 over 0, which would be the same thing as 0 over 0. I'm going to leave that one alone. So we'll just leave that as limit as theta over 0 of sine theta over 0, sine theta over theta. And there is nothing to plug 0 in for theta over here. There are no thetas, so that means that just equals 1. Well, notice, I know that this cosine is less than sine theta over theta, which is less than 1. But at this particular value of theta as it approaches 0, both the bottom and the top equal 1. Therefore, this also has to be equal to 1. Using this squeeze theorem, we end up with a real funky little corollary that's kind of cool. So, therefore, this, even though if I plug 0 in for theta, it looks like it should be 0 over 0, but it turns out, because of the squeeze theorem, it actually has to be equal to 1. And there's another trig identity that's really cool as well, and we're not going to prove that one. It's very similar. It's got a very, well, it's a different type of proof, but it's same idea. Where if I were to take this one, in my mind, this one's a little bit more boring, but it's still the same idea. And I divide that by theta, that actually equals 0. So what we're going to do here, friends, is we're going to go ahead and play with a few of these, and then we'll go ahead and we'll call it a day. So let's go ahead and clear this out here. So you don't ever need to remember that proof, but I want you to remember that that squeeze theorem, it really did a lot for us. It allowed us to be able to prove some things that are a little bit different. So the limit as theta approaches 0 of sine theta over theta. We just proved that as being 1. We also could have done a similar proof, and we would have shown that this right here, 1 minus cosine of theta, that would have been equal to 0. So what can we do with this? What if I asked you guys to try something like this? The limit as x approaches 0. What if I asked you to do something like tangent of x over x? Could you evaluate it? Well, if we plug it in there, tangent of 0 would be 0. I end up with 0 over 0. So again, I end up with something that is indeterminate form. So if it's indeterminate, no harm, no foul. That means somehow I might be able to manipulate it to get it into a different form where we can actually do it. And this is about the most trig we'll do for the entire year. You got to know your unit circle, and you need to know that tangent is about sine over cosine. That's about it. So I'm going to bring out this 1 over x here. And I'm going to make this tangent sine over cosine. And actually, I should have wrote that one more time there before I did that. Can't manipulate it quite yet until I first write it. Now I can manipulate it. So the limit as x approaches 0. I'm going to move this out in front. So this 1 over x, and I'm going to make this tangent of x. And tangent of x is the same thing as sine over cosine. So as x approaches 0, I can make this 1 over x times sine over cosine. And since we're doing multiplying, when you multiply, order doesn't matter. Well, how about I just change that up a little bit? And I end up with sine x over x. And I end up with 1 over cosine. Well, now I'm dealing with a couple of things that I actually can do. So using my arithmetic rules of limits, I can make this limit be both these guys. So limit as x approaches 0 of sine x over x times the limit as x approaches 0 of 1 over cosine x well, this right here, this whole value, that's 1. And I'm multiplying it by the limit of 1 over cosine of 0. So cosine of 0 is 1, so that's 1 over 1, which equals 1. So that means this whole limit right here of x approaches 0 of tan x over x isn't 0 over 0. It turns out it equals 1. So we're going to play with some of these other ideas. I mean, if we wanted to, we could call that a different theorem, but we don't need to. It comes from this corollary up here of the squeeze theorem. So why don't you guys try something that looks like this? What if I give you the limit as x approaches 0 of sine of 5x over x? Why don't you guys go ahead and pause the video and see what you think, try to see what you might be able to do with that. All righty. So we plug it in. Sine of 5x over x. And if we plug 0 in there, we get sine of 0, which is 0. So we get 0 over 0. So we find something that doesn't work. It's indeterminate, which again is totally okay, which means we just have to change the form a little bit. So I'm going to start with x approaches 0. And I have to figure out some way to make this match up. Now I want you to think about something here. Notice before, when we're doing this corollary, the angle and the denominator have to be equal. Well, right now, my angle is 5x, but my denominator is just a single x. I need this to also be 5x. So what I'm going to do is I'm going to multiply the top and the bottom by 5. And if I were to do that, I end up with the limit as x approaches 0, 5 times sine of 5x all over 5x. And we said again that these carry the same properties of arithmetic. So if I have a little scalar multiple here, multiplier, I can just go and bring that out front. Because whether I multiply the limit by 5 or before or after doesn't matter, because multiplication, the order doesn't matter. And by bringing that 5 out, I end up with sine of 5x all over 5x. And again, this whole thing right here, that whole thing is equal to 1. So I have 5 times 1. And that whole thing would be equal to 5. So this limit then, as x approaches 0, sine of 5x. Now you got to be careful to do your math right. Some of you guys are going to want to just take that 5 out of the angle. You want to take this 5 out of the angle. That is no bueno. That is bad. Do not do that. Cannot break. Take an angle out there. All right. Well, let's try. If you guys try one more here. See if you make sure that you guys kind of have this idea. So I'm going to have sine of 2x all over 3x. Why don't you pause the video and see what you come up with. All right, so if I plug 0 in there, I get 0 over 0. Well, that wasn't so hot. So I'm going to go ahead and see if there's something that I can possibly do here to help myself out. So right now I know I have sine of 2x, and I have 3 times x. Well, I need that bottom to be 2. So right now it's 3, but I need it to be a 2. So I need a 2 down there. So I'm going to multiply the bottom by 2. But if I multiply the bottom by 2, that means I need to multiply the top by 2. And if I were to do that, as x approaches 0, I get 2 times sine of 2x. And I have, again, order doesn't matter. So I'm going to just switch that order, make it 3 times 2 times x. And so again, I have a scalar now that I don't need anymore. So I'm going to move that out to the front. So 2/3 times the limit as x approaches 0, sine of 2x all over 2x. And so again, here's our squeeze theorem. That's our corollary of our squeeze theorem there with the sign. We get 2/3 times, and that whole thing then is going to be equal to 1. So it is 2/3. So we have limit as x approaches 0. Now, and again, notice I did not factor out my 2 from the sine 2x. I had to leave that 2 in with the x in the angle the entire time. Can't touch the angle. So whatever that coefficient is in front of the x in the angle of my sine, that's what I had to make my denominator into. And that brings us to the end. All right, gang, good luck. All right, I'll get a little trig in here. Let's see how you guys do.